In this lesson, we are going to take a look at exponential models. So this is the more algebraic side of our exponential functions. In the last lesson, we were looking at the graphs of exponential functions. Now we want to use exponential functions as a way to model real-life situations so that we can find answers to real-life kinds of problems. So here's the exponential growth model. This could also be the decay model that we talked about in class, which is that y equals a times b to the x. Now, in this case, this would be the model that we could use if we were talking about growth that maybe said was doubling or tripling, or if they tell us that we want half as much each time. If that's the kind of information that we're getting, then this is the form of the model that we want. But that's not usually how exponential growth or decay are actually communicated. Usually, instead, they tell us that things are growing or decaying by a certain percent. So a certain rate of growth or rate of decay. And so we want to take this y equals a times b to the x model and expand it so that it fits that situation where we're told the rate of growth or decay by a percent. So notice here in this new equation that we really are keeping the same pieces that we had up here. We're just tweaking them a little bit. So we still have, get rid of some of this here. So we still have our a value right here. And the a still represents initial amount. So this is still whatever amount we're starting with before the time kicks in. But now for our growth factor, instead of using the b here, we're actually going to use a growth factor of 1 plus r. So the 1 is just part of the formula, and the r here is going to be the growth rate, which has to be some number between 0 and 1. So that number is going to come from your percent. If they tell you something is growing at a rate of 10%, then we're going to change that percent to a decimal. That decimal now will fit this criteria of being between 0 and 1, and that will be our growth rate. When we put it into this parentheses and add it to the 1, then that whole base becomes our growth factor. And because we're adding it to the 1, let's get rid of some of this pen chip here so we can see again. So because we are adding that r value to the 1, that does indeed give us a base that is bigger than 1, and so we do definitely have a growth situation here. And then the one other slight difference is that instead of using x as our independent variable, we're now using t, because the independent variable is usually some reference to time. Now, because we're talking about growth in this situation, we need to end up with a base bigger than 1, so we take the 1 plus the r. But what about when we want decay? Well, since a decay model has to end up with a base, so again, here's our base, here's the parentheses that represents our base. For a decay model, we need a base that is between 0 and 1. So now, instead of adding the r value, we subtract it from 1. That way we end up with 1 minus r being something between 0 and 1, which will then give us decay. So again, the r represents the decay rate. So if we're told that something is decaying at a rate of 5% for each time period, then again we change that percent of 5 into a decimal of 0.05. That becomes the r, which is now between 0 and 1, and we subtract that from the 1 to get our base. Okay, everything else is the same. We still have that A out here as our initial amount. We're still taking this base raised to the t power. It's just that we're now subtracting the r instead of adding it. So let's take a look at a couple of quick examples. In this example, it says the owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought this car in 1984 when its value was, sorry about there, typo there, when it was $11,000. The value of the car increased at a rate of 6.9% per year. Write a function that models the value of the car over time. All right, so we've got some key information here. First of all, we know he bought it in 1984, and at that time when he bought it, it was worth $11,000. From that time until now, when he's selling it in the auction, it has been increasing at a rate of 6.9% per year. Okay, so with all of that information, the first question we want to ask ourselves is, which model should we use? Well, since we are told that we are increasing, we want to use the growth model. And since we're told we're increasing at a particular percentage rate, we want to use the model that has the 1 plus r in parentheses. So y equals a times 1 plus r to the t value. That's the model we want to use for this case. Then we need to decide what is the initial amount. So at the time that he bought the car was worth $11,000. So that's the initial amount for our situation. And then the growth rate is this 6.9%, but we're going to change 6.9% into a decimal of 0.069. Okay? So now if we plug all of that into our model, we get an equation that looks like this. Y equals, here's our 11,000 for the initial amount, here's our 0.069 for r, and we put that in to get y equals 11,000 times 1 plus 0.069 raised to the t power. Now that we have that equation, we should be able to figure out what the value of the car is at this auction. So if the auction took place in 2004, that would be 20 years since 1984 when he bought the car. So we can now plug 20 in for the t value and then work this out on our calculator to find out that the value of the car at the time of the auction is about $41,778. Okay, so that's an example of exponential growth. Let's take a look at an example of exponential decay. So this is a very typical type of problem. And again, sorry, we've got a little typo there. Try to get rid of that E. All right, so you buy a new car for $24,000. The value of the car decreases by 16% each year. Write a function that models the value of the car over time. Okay, so again, we want to look at our information here. We've got $24,000 when we buy the car. We've got the fact that it's decreasing at 16% a year. And so when we're asking ourselves which model we should use, we're now going to use the model where we take 1 minus r, because we are decreasing in our value, so that tells us we have decay, and we're being told at what rate in a percent. So y equals a times 1 minus r to the t power is the model we use in this case. The initial amount is the $24,000 that we bought the car for, and our decay rate is our 16%, which we're changing to the decimal 0.16. So when we substitute that into our model we end up with y equals 24,000 times 1 minus the 0.16 and still raised to the t power. Now, what is the value of the car 3 years later? Well, now we're looking for 3 years as our time. And so when we substitute that into our model that we wrote here, we'll see that the value of the car 3 years later is about $14,225. So once you are able to set up these models here, then you can put in any particular time that you're interested in, right there, and you can find out the values or what the growth or decay numbers are by just punching it into the calculator. These will be considered application problems, so you will be allowed to use calculators to work them out and get the answers that are being asked for. All right, so we'll talk about this a little bit more in class and go through a couple more examples there to make sure you understand how to set these up and work them out on your calculators. Make sure if you have questions that you ask about them in class. Otherwise, we'll see you next class.